here we're going to have a look at some strong and weak acids and some strong and weak alkalis. We're going to have a look and see what makes something an acid, what makes it strong. So let's have a look and see what we can try and have a look at with some of these things. The acids are basically measured in a scale we call pH. So are alkalis. But basically, what is it? What does pH mean? So let's have a look and see what that is. Alright, so this idea about pH, well, it's a peculiar sort of scale, and basically it's related to the concentration of an acid. And what is an acid? Well, it's something that contains these things: hydrogen ions. So we're looking at the concentration of hydrogen ions, and the way it works out, that if we've got a concentration of 0.1 moles of H plus ions, we're going to call this pH 1. If I've got a tenth of that, 0.01 moles of hydrogen ions, then we're going to call this pH 2. Similarly, if we've got a tenth of that, 0.01 moles of hydrogen ions, this is going to give me a pH of 3, and similarly, and we go on, 0.0001 moles gives me pH 4. So as the concentration of hydrogen ions gets less, we call it a weaker acid. There are less of these hydrogen ions to react with. So let's have a look at some strong acids and some weak acids, and let's see what we can find out about what they do. So let's go over and have a look at some of these substances. Okay, we've got then a real collection of bits and pieces here. I've got 3 acids here. Now they're all the same. Let me zoom in here. So I've got 3 different concentrations of hydrochloric acid. We've got a 0.1 molar, a 1 molar, in other words 10 times as strong, and we've got a 2 molar, which is standard sort of solution. We've got some other acids we can have a look at. We've got 3 acids here, all the same strength. This is hydrochloric acid, sulfuric acid, and nitric acid, called the bench acids or the mineral acids. I've got a variety of other acids. I've got acetic acid, and then I've got some different acids here. Ascorbic acid, otherwise known as vitamin C. Push them along a bit. Citric acid from citrus fruits, and acetic acid, which you probably know better as vinegar. This, of course, I've got in different concentrations. I've got another one of these. I'm not going to use that one today, which is called glacial acetic acid. As strong as it can get, acetic acid. So let's start off with a very simple idea about what we've got. So let's zoom out a little bit so you can see what's going on. And first of all, we're going to do a very dangerous experiment. And if I'm going to do one of these, then I really ought to put my safety specs on. This is citric acid, and I'm going to now do something which I would not recommend anyone to do, and that is I'm going to stick my finger into some acid. And we stick the finger in the acid and we start to feel the pain as the acid starts burning away into my finger. And let's take it out and just dust off any odd bits of citric acid that were lying around. And it's not affected my finger in any way. But this is dangerous stuff. But it's not dangerous here. Why isn't it dangerous here? Well, it's not dangerous here because citric acid is not an acid when it's a solid. Because I said it's all about the concentration of hydrogen ions, and my concentration in solids is a bit weak, really, if that makes sense, because there is no solution, so there are no hydrogen ions, and if there are no hydrogen ions, then that isn't acidic, so therefore it doesn't appear to be very dangerous. So if I put some universal indicator paper in here, we find that nothing happens. I'm not even going to bother doing it really, because I just put it in there, I leave it just like my finger, nothing happens. And it takes a while for nothing to happen, so I'm not going to do this. But what I will do is I could take some citric acid and I could take a small sample of that and put it into a test tube. So let's get myself a test tube rack and a test tube, and let's now take a small quantity of citric acid, and hopefully, yeah, you can see it's just a small quantity that I put in the bottom of the test tube, and we'll add a little bit of water to that, and I better be good and put that back, and let's shake it and get it dissolved. It dissolved quite readily. And do I fancy putting my finger in there? The answer is no, I don't, because that is now quite acidic. And what we need to do is we need to put in some universal indicator. And cleverly I put that on the table, so I have to go and get it. Bit of universal indicator. We know from universal indicator reds are acids, so let's try this one. Let's just put in a little bit, and we can see immediately that has gone really quite a strong red colour. So that is very acidic, and I wouldn't fancy putting my finger in there. Another one of these acids that we come across is this one, ascorbic acid, and this is L-ascorbic acid. There's another variety called D-ascorbic acid, left and right, and this is again a solid, but this stuff is good for you. If I take a fingerful of that, I can put it in my mouth, and that is my vitamin C. Probably if I put my finger in there, it's enough for probably about, I don't know, a week or a month's amount. So I'm not going to try that one. But again, this is not an acid. I could put my finger in there, it's just a powder, doesn't do anything. Let's put it into a test tube and we'll see what this is like. So a bit of ascorbic acid. Let's dissolve that. Give it a good shake. It dissolves really readily. Let's take a little bit of universal indicator and you can see again this is an acid. If I compare these two, you can see that it's not as red, it's not as strong. We'll just zoom in for you a little bit and you can see the colours there. The ascorbic acid is not quite as strong, as high a pH. So if we're going to try and compare some of our acids, we want to have a look at them, then one of the things it's fairly important to do is make sure that we have similar concentrations to try these out. So let's have a look at the relative reactions of these three acids. We're going to look at nitric acid, sulfuric acid and hydrochloric acid, and I'm going to react those with sodium carbonate. We might be able to see a difference between the different acids. And then what we're going to try is we're going to try the same reaction but with these three acids. 2 molar, 1 molar, see if it makes any difference, and 0.1 molar, see if a tenth makes any difference. So we'll have a go at those experiments. Okay, so let's start off. And I'll get a couple of test tubes out. Alright, I'm lying to you. I'm going to get a few out. And let's have a look and see what happens with these. So let's first of all try out a little bit of nitric acid. Now it is important with all these acids to make sure that we're careful with them, but also that we use the same amount. And so I'm going to approximately do this, and I'm going to put in a little bit. And when I said a little bit, you know, we're looking at about a finger depth full of nitric acid. We're going to react that with some sodium carbonate. Now, what reaction should we expect? So let's have a look at this. So looking at here, we've got nitric acid, which is HNO3 plus sodium carbonate. So we have acid plus carbonate, and this is going to give me a salt, which is going to be sodium nitrate plus water plus carbon dioxide. So we should see a fair bit of bubbling, fizzing and carbon dioxide being produced, and that could give us an idea about how reactive this reaction is going to be. So let's try it. And what I'm going to do is put a small amount in there. Ready? Here we go. Well, that reacted virtually instantly, didn't it? Let's put another little bit in there. Have a look. And that reaction went almost instantaneously. So our reaction of nitric acid and sodium carbonate appears to be quite quick. Let's compare that with a different acid. Let's take some sulfuric acid. Again, I've put about a finger's depth in, and let's try a bit of sodium carbonate with this. Let's compare. Well, there's not much in it, was there? Let's try again. A lot more this time. And that is reacting really nicely. If I put my finger here, I can feel it's got a little warmer. Not very. Just making sure all the sodium carbonate there has reacted. So not much difference then between our first acid, nitric acid, and the sulfuric acid. Let's try hydrochloric acid. Again, I don't want to put very much in, but perhaps a little bit more than that. There we are. So I've got my hydrochloric acid, and I'm predicting it's going to be fairly similar. So let's have a look at this one. Let's plunk it in. And not much difference here between the three acids. They are all reacting, put a bit more in, very quickly with this sodium carbonate. So they're all working really quickly. So let's now try if there's not much difference between the reactivity of the mineral acids here. Let's try and compare that reactivity with different strengths. I don't think we're going to see much difference between the 2 molar and the 1 molar, but we might see some difference between this and that. We might. So let's have a look. We're going to start off with then some 1 molar hydrochloric acid. Let's take our sodium carbonate. Don't want too much. And here we go. Ready? Well, that didn't appear to be that different to this one. The 2 molar. There's your 2 molar going. There's the 1 molar going. Really not a lot of difference here. Let's see if the 0.1 molar makes any difference. Put about twice as much in there as I wanted, and what I'm going to do is I'll put that in another test tube. Right, let's try it again. So we take our sodium carbonate, and this is now 0.1. Well, did you see that? Was there less fizz? Compare it with the 1 molar. Definitely a little less reaction. So I've now got a little bit in here, and what I could do is I could dilute this. Now I've got a bit too much, so I'm just going to get rid of a little bit of this. That's ideal. And what I'm going to do is I'm going to dilute this about tenfold, only approximately. I could have done this with a measuring cylinder, but I'm just trying to give you an idea. And let's put in the same amount. So this is now not 0.1 molar, but 0.01 molar, approximately. So we've got our sodium carbonate ready to go. Let's put it in. And not much action there really. Put a load in. Not much fizzing at all. Compare that with the 0.1 molar. Little bit more. Compare that with the 1 molar. So we are seeing now a difference. 0.1 molar, not really doing an awful lot, and the 0.1 molar to the diluted 10 times, then not much action. So as we dilute the acid, it is becoming less reactive. We're seeing less going on because there are less hydrogen ions in there to do anything. Now if we dilute this more and more and more, we can start to see less and less reaction. So there are our acids. Let's compare that with a different acid. Now this is acetic acid. Now this is generally what I would term a weak acid. And this weak acid I would be actually prepared to put on my fish and chips. What we're going to do is going to have a look at how this one works. There we are. The glass stoppers aren't used so much these days because they're relatively hard to open, so we switch over to plastic ones now. Let's just put in a small amount. There we are. And if I smell this, definitely the smell of vinegar. I'm not too worried about this one because this is just, you know, vinegar, and it's the strength that you would normally put on your fish and chips. Okay, let's take this, and what I'm going to do is react it with the sodium carbonate again. Let's have a look and see what happens. And we're seeing a reaction similar to perhaps about the 1 molar hydrochloric acid. Let's take this, let's put in here the same amount, but this time what I'm going to do is I'm going to put in about 10 centimetre cubed of water, and then that's 10 times diluted. Let's put that one in there, so that's about 10 times dilution. Now we're going to cheat. 10 times dilution, let's put that one in here. So that's 1 molar, that's about 0.1 molar. Let's put in 10 centimetre cubed of water in here. And I'm starting to run out of test tubes. That is again more dilute. So we've got 1, 0.1 and then 0.01. Let's see what happens with a weak solution. So the strong again, to remind you. Slower than one of the other acids. 10 times as weak. And the reaction is not anything like as strong. Still working, but not as strong, not as fast. Now 100 times. And barely anything happening there. We could go on and dilute more and more and more until basically nothing happens. And let's see why that might be true. I mentioned earlier we had pH 1, 2, 3, 4, but many people know that we get down to 7. So if I do 0 point, and we have 3 noughts makes pH 4, so if I do 1, 2, 3, 4, 5, 6 and a 1, that's going to give me pH 7. And this, we know, is neutral. If we take water, H2O, and we ionize this, it becomes H plus and it becomes OH minus, and we've got the same amount of acid and alkali, and when that's true we've got a pH of 7. If I have more OHs than I have H's, we carry on with this scale. The H ion concentration is going down, the OH here is going up, and the pH then continues as we've got a higher and higher amount of OH ions or alkali. So what are we looking at with these strong and weak acids? Well, the difference between a strong and a weak acid isn't quite as obvious as it seems. So let's meet a strong acid. Let's take HCl. When I put HCl in water, what happens is all of it becomes H plus ions and Cl minus ions. But if I take a different acid, and let's now go for what I called acetic acid or ethanoic acid, and this is CH3, COOH, a different type of acid. This is an organic acid, and we'll call it ethanoic acid, or if you prefer, vinegar. When I put this in water, what happens is we get a different arrow being drawn here, a double-headed arrow, meaning that some's going this way and some's going that way, and I get CH3, COO minus, plus I've got H plus. So I've got my ethanoate ions, similar to my chloride ions, plus I've got my hydrogen ion, or my protons, maybe we could call them. So what's happening? Well, this reaction doesn't go all the way. This reaction, put the hydrochloric acid in water, and it fully disassociates. All of the atoms here separate. But in this case of a weak acid, some of it stays like this and some stays like that. And now we've got probably a weaker acid because we've got less hydrogen ions being present. So we see then with a weak acid, basically we can say that it is not fully disassociated. What a big horrible word. It means that all the hydrogen ions haven't been released, that some are still held up in this form. So if perhaps, let's say, 30% gets turned into this and 70% stays at that, it would only be 30% as strong as one of those acids, but at the same concentration. So a weak acid isn't necessarily one with lots of water added to it, but in fact it could be one where it does not fully disassociate. Well, let's have a look at the pH of some of these acids and see what we can come up with. So let's have a look at the pH of a few of these acids. To do this, what I'm going to do is we're going to have a look at a few of these acids, and what I've got is my pH meter, and I'm just going to stick this into some distilled water. And if we have a look at this, we should see a pH of, oh dear, not quite right. There we are, 7.02. It's not quite right, is it? My water wasn't quite 7. I'm very sorry about that one. I am just dealing with real life situations. Okay, let's try a small amount of some of these acids and have a look and see what happens. So let's take my 1 molar hydrochloric acid, and I'm going to put a little bit in there. I'm going to take some of my 0.1 acid and put it in there. Let's see if we can compare the pH. So let's record the pH. This is the 0.1. We can see this is 1.6, 1.59. Changing a little bit. Right, I'll clean it and put it back into water, and you'll see the pH will rapidly turn back to about 7. Now it won't fully do that because I've got some hydrogen ions in my little container here. So what I should do is just get rid of this water which I've used, and let's I've got some more distilled water here. Put that in there, and we're back to about 7. It's a little bit more. Odd considering it's the same amount of water I had, but still. Right, let's try this now in 1 molar. And you can see, instead of being about 1.5 as it was before, now we're down to about 1.1876. About 1.1 I reckon. It's settling down. As far as I'm concerned though, taking it out, washing it, cleaning it again, the basic idea is that we're seeing that it is less strong. And remember, the pH change of simply 1 means that it is 10 times less number of hydrogen ions. So my pH is gradually returning back as I clean this in some water. Let's see, give it a good clean, and now back in water we should see that it's about 6.7, 6.82. It's getting there. Give it a few moments and it'll settle down. So we have already seen that these are different pHs. How about something a little bit more alkali? So here I've got some lime water. It's not very alkaline. But we should see this put into there, and if we look at our alkali, we can see up to about pH 11. pH 11 and a little bit. And we'll give this a good rinse, and we should see this returning to about pH about 7.1. So I've got 3 little beakers there. We've used some acid and we've used some alkali. How about strong alkali? Well, let's compare that with a strong alkali, and I've got here some 2 molar sodium hydroxide. That's pretty strong. We've got also what's called 880 ammonia, which is very strong ammonia, and then I've also got, he says, quickly cheating and grabbing hold of something, I've got my sodium hydroxide, its friend. We've got potassium hydroxide. Now, the reason I was panicking there was my potassium hydroxide, when I got it out, actually looked like this. And you can see this potassium hydroxide looks a bit different than the other one. And we can see that down the bottom we've got some stuff come out of solution. And so we had to go and make some more up, because this doesn't seem to have a very good shelf life. Basically, some of the potassium hydroxide seems to come out of solution. So there's my old, I've got my new. Now let's try having a look and see what one of those looks like. I'm not going to do the ammonia because you can't smell how bad that smells, but we can here, and the vote was not to do that one today. And we can have a look at either potassium or sodium hydroxide. There's not a lot in it. We've got some nice new potassium hydroxide. Let's have a look and see what this is. And we're up at about 12.6. It's going to usually hit 12.6. There we are. And probably 12.7 here. There we are. About 12.7. So there is my potassium hydroxide. Well, would sodium hydroxide be any different? Well, it probably would. So it's probably worth having a look at this. So I've cleaned my pH probe and it's down to about 7.3, probably going down to 7.1 again. So it's getting right. And what I want to do is look at a little bit of, this time, sodium hydroxide. I've run out of little beakers. Let's have a look at this one. And that one, not quite as strong. pH 11, there we are. just finish off with cleaning up my pH probe. Giving it a good wash. And we can see that is down to about what it was before, about the 7. We've probably still got some other ions in there. And then when I finish with my pH probe, then what I'm going to do is I'm going to store it away safely, and what we're going to do is just pop it into a solution, and this solution is about 4 molar potassium chloride. So there we've had a look at some stronger acids, some weaker acids, and I suppose the only one we didn't look at was acetic acid for you to have a look at. I suppose I could be persuaded to do this one, having just put my pH probe back. I forgot it, so let's just do it quickly, because otherwise people will be wondering about it. So I've got my pH probe. It's sitting there at round about pH 7. Let's put it into this acetic acid. And you can see that it is still quite strong. So there we've got it about 2.6 pH. Just got a fair bit of dirty water here that I'm washing this in first, and then I can wash this in a little bit of cleaner water, and we should get this pH probe going back to about 7 before I put it back in the potassium chloride solution. 6.6. There we are, it'll do. And I'll push that in, lock it in tight, and that will keep this pH probe in working condition. The pH probe does need to be calibrated every now and again, and what we do with that is I put other solutions. So I've just taken the safety specs off, and what we can do is try this in different sort of what we call buffers. So before I start, we eventually got the right screen there. Then what I can do is I can test my pH probe, and I put it into a known acid, and then I can put this into a known alkali, and when we've done that we can say, well, we know this is pH 2, and I can adjust my meter, so my pH probe, so it does read pH 2, and then I can put it into a known alkali, which is perhaps pH 10, and I can secure what they are. Having left my pH probe, you'll see now it's gone happily back to pH 7.2. So it's about right for the water. One more. Don't know why I always sneeze in threes. So we've had a look at some strong and some weak acids. So we've now got an idea about the difference between those. I hope you found that useful. I hope that's given you some idea about the difference between strong and weak acids, and an idea about some alkalis as well, and how we can measure them with pH probes. pH probes come in all sorts. There are small handheld ones to super duper accurate ones. Next time we'll start having a look at electrolysis, which is one of my favourite subjects in chemistry. Until then, if you found this useful, then please subscribe, and I hope to see you next week when we'll have a look at some more GCSE chemistry, going through it topic by topic. Stay safe. Bye bye.